I'm just doing, there you go. Okay, I hope you can see my screen now. That's fine. Okay, perfect. So thank you, Gabriel. And I'm very happy today to present my PhD research at the CTG online seminar series. Before starting, actually, I would like to thank some people, especially my PhD supervisor, Pascal Audet, Andrew Schaefer at GSC at the Geological Survey of Canada, Jeremy Goslin at University of Ottawa as a PhD and is going to graduate very soon in a matter of days now. Rick Astor and Derek Shutt at Colorado State University, and Joel Kubley at UConn University. And so today I'll be presenting my PhD, which is the evolution and dynamics of the lithosphere in northwestern Canada. And I think it's great to start with an overview of the tectonic of the region. So here on the left, you have a well-known map of the terrains that were created onto the Laurentian margin at different times in northwestern Canada. As you can see, it looks like a patchwork of different colors. It's because they have different affinity and different timing of creations. And if we go from east to west, basically there are different super terrains, so big groups of terrains. The first one from the Cordillera Deformation front to the Tintina Fault is basically a super terrain that has affinity with the North American Craton, so sharing characteristics, geological characteristics with the North American Craton here. Between the Tintina and the Denali Fault, we found the intermontane super terrain with the Cassiar terrain, for example, which is a sleeve of ancestral North America that is stuck against the Tintina Fault here. Further south, we have younger terrains that are part of the Insular and the Albord superterrain, and especially the Yakutat block, which collided the margin of North America 25 million years ago. And as I mentioned, there's a number of faults there. The Northern Canadian Cordillera is heavily faulted, and three of them are the main ones, such as the Tintina Fault, the Denali Fault, and the Teslin Faults that are on this slide here. The three of them produce 800 kilometers of horizontal displacement between Lake Cretaceous and the ocean, so it's a big amount. And the Tintina itself produces 430 kilometers approximately of horizontal displacement based on geology recordings. And so here during this talk, I'll be presenting the northern Canadian Cordillera, and by northern, I mean the northern part of the Canadian Cordillera. And what is the northern Canadian Cordillera? It's defined, basically the southern bound is defined here at the Yukon, British Columbia border, roughly. And it corresponds also to a change in seismicity. If you look at in the southern Canadian Cordillera in British Columbia, there's not a lot of seismicity in the interior of the southern Canadian Cordillera. But north of the border, here there's quite a lot of seismicity in the Mackenzie Mountains with magnitude 5s occurring, and also in the Richardson Mountains, which is quite surprising because we are like 8 to 1,000 kilometers away from the plate boundary here. There's not also a lot of seismicity around the Tintina Fault here, which is quite surprising because looking at this feature, it's massive. There's quite a lot of seismicity on the Denali Fault, which produced like some largest earthquakes in northwestern America with the 2002 earthquake here, and obviously lots of seismicity at the plate boundary with the collision zone between the Yakutat block and the margin. And so this figure here highlights the questions that we are going to look at during this presentation, such as like, why do we have seismicity here in the Richardson Mountains and in the Mackenzie Mountains? And if you look at the shape of the Cordillera Deformation front here, it's linear in the southern part of the Cordillera here, the Canadian Cordillera, and it's quite arcuate here around Mackenzie Mountain, First and Fault Belt. That's this part of the Cordillera Deformation front. So that's a bunch of questions that we're going to investigate during this presentation. But before going to any results, it's good to highlight some work that had been done in the past, especially from the LITHOPROBE SNORCLE lines. So that was a project, an experiment that was running in the late 90s. And here you have the locations of the 3 different lines that were going through the Cordillera and the Canadian Shield here. And I won't go through the entire details of the LITHOPROBE SNORCLE lines here, but just to mention that, as you can see on this profiles here, the moho is very flat along the transect. There's not a lot of topography. And so the main takeaway, there's two main takeaways, is that the crust is thin and that the terrains were thrust over a North American basement in the region. And since then, we have a number of different geophysical models, for example, with the different potential field methods, with the model from Fluke et al., where they were looking at the effective elastic thickness, which is a proxy for the strength of the lithosphere. And what they were seeing is that the Cordillera is, as a lithosphere, is quite weak compared to the adjacent Craton. If we look at the study from Edis-Gaudreau et al. In 2019, they were looking at the Curry depth point in northwestern Canada. And what they were showing here is that the Curry depth point is quite shallow in the Cordillera west of the Tintina fault and quite deeper into the Slave Craton here, for example. And that's a proxy for temperature. The shallower the Curry depth point is, the hotter the crust, basically. There were a number of teleseismic body wave models that were developed taking advantage of deployment of temporary seismic networks, such as the model from Fredrickson et al. In 1998 or Mercier et al. In 2009 with the canoe array here. This is this Y-shaped array here. And what they were showing here at 100 kilometers depth is that in the Craton is characterized by high velocity anomalies, while the Cordillera is more characterized by low velocity anomalies, basically. And obviously, more recently, there were a number of surface wave models that were developed, for example, and published, like the one from Schaefer and Lebedev in 2014, which was describing the seismic velocity structure of North America at the continental scale. And you can see that basically we have high velocity anomalies across the Craton, the Canadian Shield, and way lower velocities and velocity anomalies in the Cordillera, reflecting basically two different tectonic domains here. And same with the model of Zaporazan in 2018, and that was kind of a low resolution model, but that was showing this low velocity, uniform low velocity anomaly over the northern Canadian Cordillera and high velocity anomaly to the adjacent Cratonic lithosphere. And so the main takeaway here is that the lithosphere in the northern Canadian Cordillera is quite thin, hot, and weak compared to the adjacent cold Craton. And so we have a number of different models. And here is some work from Roy Heinemann and colleagues. And they noticed that from the SNORCLE lines that the moho is very flat and shallow. And that goes against the theory of hairy isostasy, basically, because wherever you have mountains, you would expect to have a thick crystal root. But that's not what we see in the Canadian Cordillera. So here, if you look at this cartoon here, and this is here the Craton, and this is the Cordillera here. We have a moho at 40 kilometers depth in the Craton, and if you apply this the airy theory, you would expect to have the elevation almost just right above the sea level. Again, if we do the same in the Cordillera, the elevation should be below sea level, but that's not what we observe. We observe that on average, the elevations are about 1,000 meters above sea level. So there's need to be something else. There's need to be something else that explain such elevations. And that is provided through thermoisostasy, where you have the thermal expansion of hot mantle rocks that support and sustain high elevations at the surface. And now let's imagine that we have a very high temperature at about 900 degrees at the moho. Then at such temperature, you'll be able to develop some zones of weakness within the lower crust, where you have partial melting, for example. And so if we have some zones of weakness, well, then you can envision a way where you could propagate stresses from the Yakutat collision zone towards the Canadian Cordillera interior, such as the Mackenzie Mountains, for example. And that was modeled by Stefan Mazzotti in 2002 in their geology paper here. So you have a transect going from the Yakutat collision zone, so from the plate boundary toward the Canadian Shield, going through the Mackenzie Mountains. And so their model showed basically that you could transmit stress over this, what they call lower crust detachment, so some weakness into the lower crust, and that would reactivate basically weak thrust fronts at the Cordillera deformation front. And so this foreland rig zone here is supposed to mimic the Mackenzie Mountains here. Obviously, there were other models that were proposed and published. One of them is this model from Emily Finzel in 2015, where she combined different geophysical data set in order to model the basal tractions. So here, the field of arrows that we see represent the tractions, and the length, the magnitude of the arrow gives you an idea of the traction in megapascal. And what we see is that this basal traction here is basically a proxy for upper mantle flow. And we would have some southward motion from Alaska that will be deflected around the Aleutian subduction zone, the Yakutat subduction zone here, toward the northeast and toward the Mackenzie Mountains. That's another way to drive stress and deformation in the northwestern Canada. And so during this presentation here, I'm going to ask several questions. So what's the nature and the origin of the lithosphere underlying the Northern Canadian Cordillera? So first, how does crustal structure influence current tectonic activity in the Northern Canadian Cordillera? And second, what's the mantle seismic expression of the main fault zones across the Northern Canadian Cordillera? And lastly, how was the Craton margin modified during the Cordillera orogeny? And so in order to answer those questions, we're going to employ seismic tomography and seismic anisotropy. So seismic tomography is going to give us an idea of the seismic velocity structure. So through development of teleseismic body wave tomography and surface wave tomography models, while the seismic anisotropy is going to give us an idea of the dynamics of the upper mantle with the SKS splitting analysis. And so I know that in the audience, there's not a lot of geophysicists now. So I'm going to skip all the details about the method. I just have some slides, just 2 or 3 slides to give you a rough idea of what we've done here. But basically, the surface waves, they sample medium along surface paths as shown here. So short periods are going to be slow and longer periods are going to be faster. And so the surface waves have a good depth resolution and variable lateral resolution. And in surface waves tomography, that would depend, for example, on path coverage. For the SKS splitting analysis, it's mainly sensitive to anisotropy, seismic anisotropy. And this is very good for detecting upper mantle seismic anisotropy. And I'll get back to that a little bit later in the presentation. And also just to mention, that gives you just a point measurement beneath the station. And for teleseismic body waves, they sample medium along rays. It has very good lateral resolution, but a poor depth resolution because of the geometry of the rays. They come almost with a vertical angle. They're almost vertical beneath the station, so it allows for vertical smearing. And so this PhD was motivated by the recent deployment of temporary seismic networks across northwestern Canada. And as you can see here, you have different snapshots of the station coverage across northwestern Canada. Each triangle represents a seismic station, and they're color-coded by network here. And you see that in the last 6 years, there was a rapid increase in station coverage with, for example, the US RTA stations, that's the light purple triangle, the MMP transect here, Pascal-Odé's network here, which are represented by these triangles across the Cordillera, among others. And so this data set here allows us to develop tomographic models which eliminate the 3-dimensional seismic velocity structure of northwestern Canada at a higher resolution compared to previous studies from the crust to the upper mantle. And so I decided to split this presentation in 2 parts. I'll focus first on the crustal structure using the surface wave tomography model, and then onto the upper mantle seismic structure after. So here, just a few bullet points about the method that we used. So we use this 4-step procedure. It's quite common in geophysics and seismology. So you first pick fundamental mode Rayleigh-wave group velocity dispersion from regional earthquakes. So those regional earthquakes are shown on this figure here to the left with these red stars. They are a magnitude 4.5 and greater, and they all occurred between 1993 and 2019. And here we employ the transdimensional Bayesian tomography method from Jeremy Gosselin in 2021, which inverts for azimuthally anisotropic group velocity maps. Then we extract dispersion curves at each location and invert independently for shear wave velocity profile in a probabilistic framework. And here we use also MOHO depth priors from receiver functions because surface waves are not great to image discontinuous structures such as the MOHO. So it's always good to have some over information such as the MOHO estimates from receiver functions. And finally, we just stitch together the different depth profiles and we get a pseudo 3D VS mode. And that's what I'm going to show. So first, I'm going to show you the isotropic component and the anisotropic component of the final solution of the group velocity maps here. So to the left, we have the isotropic component of the group velocity maps. Careful that the ranges, they change from one figure to another. They go from 10 to 50 seconds. So basically, the shorter the period, the shallower the medium you sample. So for example, 10 seconds and 20 seconds would be sensitive predominantly to the crust, while 36 and 50 seconds will be predominantly sensitive to the uppermost mantle. And here, I'm not going to discuss those maps because they have some weird sensitivities. The group velocities have weird sensitivities. They have a negative sensitivity, which makes them very complicated to interpret compared to phase velocity maps. So we need to develop a 3D model in order to say and to see where those anomalies are at depth. But still, what's interesting is this anisotropy maps here. And you can see, so for the 10 and 20 seconds, we have in red, each red bars represent the fast axis orientation of the surface waves here. And the length of the bar gives you an idea of the percent of anisotropy. And what we see is that the fast axis orientations tend to align with the main tectonic structures. So they are northwest, southeast, just like the main tectonic structures like the Tintina, Denali, and Teslin faults. And also what's interesting to note, it looks like they tend to wrap up around the Cordillera deformation front here in that location. And then they tend to rotate in northern Yukon to be southwest, northeast. And that's something that we still see at longer periods, 20 seconds. And I'm not going to detail those maps because they're sensitive to the uppermost mantle. And so after you get your group velocity map, as I said, you can extract for each location your dispersion and invert for a 1D profile. And so then you stitch them together. And that's the kind of model that you can get, a pseudo 3D model. So you have depth slices running from 5 kilometer depth to 40 kilometer depths. And again, carefully here, the shear wave velocity ranges from 3.1 to 3.7 here to 4.1 to 4.6. So they are all different. And so if we look at the very shallow part of the crust, so 5 kilometer depths, we see that there's some regions showing low velocity anomalies, low velocity regions, and they correspond very well with the sedimentary cover, especially here where we have, oh, close my pointer. Yeah, here where we have the northwestern end of the Western Canadian sedimentary basin, which is about, I think the sedimentary cover is about 6 to 7 kilometers depth. And here in the Richardson Mountains, we have also a thick sedimentary cover. So that's great that the model is able to pick up the signal because shear wave velocities will travel slower through sediments. Also, here in the Canadian Shield, you know that we have this broad high velocity region, and that corresponds, I think, to the igneous and metamorphic rocks that consist of the Canadian Shield. And same for the Canadian Cordillera here, these regions correspond to, I think, the crystalline basements. That's what we see. And as we go deeper into the mid to lower crust, we see that there's a drastic change. And now we have a very slow shear wave velocities across the Cordillera, especially from the plate boundary to the Mackenzie Mountains and to the Cordillera deformation front. And that's quite remarkable that it stops right where is the deformation front. And there's a clear dichotomy between the Canadian Shield and the Cordillera here, with high velocities in the Canadian Shield and low velocities within this portion of the Canadian Cordillera. At 40 kilometers depth, here what we see is just a reflection of basically the MOHO topography. So regions that shows high velocities you're already in the upper mantle, while for the regions that shows slower velocities, you're still in the crust, just above the MOHO. And so, yes, we also invert for the MOHO here. And so, as I said, we use prior information from the other studies, receiver function studies. So each dot here represents a station for which we have a MOHO depth estimate here. And then I just linearly interpolated between those points to obtain this map in the background. And so that is the input to the inversion. And that to the right here, the top right, gives you the output MOHO depth that we get from the inversion. And so the main differences are in the oceanic parts of the region. So in Gulf of Alaska here and also in the Balfour Sea. And that's because there's no OBS deployment. There's no stations there. So there are just the input MOHO depth here was just basically nothing. It's meaningless because there's no data that was just linearly interpolated. And here you see that the inversion code is able to pick that the MOHO is super shallow. It's about 10 to 15 kilometers, which makes sense with an oceanic crust kind of. But we note also that there's other differences. So for example, here we have the MOHO depth difference between the output and the input. And we see that the most slightly, pretty slightly deeper MOHO depth estimates in the Canadian Shield, but also in a northern Yukon and between the Tintina and the Denali Fault. And it predicts a shallower MOHO in the Mackenzie Mountains. And here bottom right is just the standard deviation from the PPD, so from the probability density function of the MOHO depth estimates here. And so we note that, okay, the distribution of MOHO is quite narrow. It's about 25 to 40 kilometers if we consider just the Cordillera. And the average value is about 33 kilometers. So that's quite in agreement with the estimates from the SNORCLE lines. But we note that some regions shows relatively deeper MOHO, such as here in northwestern part of the Mackenzie Mountains. And that was interpreted to reflect maybe the stacking of different crusts of acute terrains, that they were stacked here against the Cordillera deformation front. And that could have like a Laurentian or origin, or that could be of the Cordillera origin. Another region where we have a deeper MOHO is here, south of the Denali Fault. That's what you would expect where you have a collision zone, because you have the Yakutat subduction zone. The Yakutat has flat subduction with a flat subduction here. And so you will expect a crustal thickening. And so that was what we see here. So that's kind of cool. Yeah, so we have quite a narrow distribution here for the MOHO depth values, but we've saw some variations here across the Cordillera. And so here are some cross-section view through the mole from the surface to 100 kilometers depth. And we will just focus here on the first, on the crust. And the BB prime transect is here, north-south here. You have the C prime and DD prime, which run perpendicular to the main structure here, the Tintina and the Denali Fault. And so what we observe here, if we just focus on the velocities, it's that we have lower velocities across the Cordillera in the lower crest. That's what we see here. And then you see that in the Canadian Shield, we have higher velocities here. And it looks like there's some features here going on with at greater depths. And here along BB prime, so going through the Cordillera, we see that there is higher velocities in the lower crest in northern Yukon. And again, DD prime, we see that below the Mackenzie Mountains, there's this region of low velocity here, and then a higher velocity in the lower crest there. And just to mention that the black dashed line here is the input MOHO, and the white dashed line is the output MOHO from the inversion. So in another way, here we show that the lower crest of the Northern Canadian Cordillera is characterized by low velocities that extends from the Pacific North American plate boundary to the Cordillera deformation front. We have a shallow MOHO across the NCC with some variation, but the distribution of MOHO values, or MOHO estimates, is quite narrow, with an average about 33 kilometers depth, 33 kilometers, sorry. And so those 2 points here are quite consistent with the orogenic float mole from Einman and colleagues in 2005, and Aldo and colleagues in 1990. And so what we think we see here is that there's anomalously low velocity regions in the mid to lower crust within the northern Canadian Cordillera, reflect the widespread elevated temperatures beneath the Cordillera that could generate lower crystal flow, and that would brilliantly support the high elevations of the region. However, we are not able to pick up the signal of a lower crystal detachment because, as I said, surface waves are not great to pick up like such discontinuous structures, especially that a detachment will be a very, very thin, you know, like it won't be a layer, so thick layer, so it will be hard to see that with the surface waves. So we can't really discard it, but we don't see it so far. So now we'll dive into the second part of this presentation, which is about the upper mantle structure in northwestern Canada. And so this part will be more focused on the teleseismic tomography moles. So here by teleseismic, I mean that we use far distant earthquakes. So for example, here, earthquakes that occur in Japan or South America and other places. In order to construct this mole, we used a well-known method from John van der Kaarten in 1995, which is the regularized and isotropic least square inversion method, which inverts for slowness perturbations, station, and even correction terms. And so here we used a very large data set, which consists of more than 127,000 and 60,000 P and S wave relative delay times. And so we obviously use all available stations, as you can see on this map here, including all the US array TA stations. So they are in dark blue here across Yukon and Alaska, YNSN stations in green, that's Pascal station, stations. The Polaris stations that are no longer there in the Canadian Shield, and the CNSN stations that are in cyan. And to the right here, you have a ray density map at 200 kilometers depth. And so basically blue and purple colors would show very dense ray across a dense number of crossing rays within an element of volume within a mole, while red to green colors would show basically the opposite. And so what we see is that at 200 kilometers depth, we have quite a good ray density through the northern Canadian Cordillera, especially this part of the northern Canadian Cordillera. So here we followed a classic trade-off approach where I had to play with different level of regularization, because here this problem gives you a non-unique solution. So you need to apply some constraints onto the set of equations that you have. And so that's called regularization. And you play with a different level of regularization in order to explain different level of data misfit here. And you pick the mole that lies within the maximum curvature, the trade-off curve. But that's all I'm going to say about that. Here is our preferred mole. So that's the Teleseismic P-wave mole again. So Teleseismic far distant sources at different depths, 4 different depths at 100, 150, 200, and 300 kilometers depths. That's P-wave velocity anomaly ranging between -2 and +2%. So basically red colors means slow and blue colors means fast. And so if we compare that with our Teleseismic S-wave mole, so that's the same thing, but now the S-wave velocity anomaly ranges between -3 and +3%. You see that they're quite common, that the main features are present in the two moles, such as the high velocity region here in northern Yukon, low velocity region here, low velocity anomaly here, high velocity here, and so on. So that gives us confidence in our final results, because we invert them independently. You know, they were inverted independently. And now if we compare them with our surface wave tomography mole, so that extends from 50 kilometers to 100 kilometers depth. So that's basically the very shallowest part of the Teleseismic P-wave mole. So that's kind of complementary in a way to the Teleseismic P and S-wave mole. And so what we see, for example, at 100 kilometers depth, that's what we can compare, is that we'll observe some features that here too. So for example, in northern Yukon, we have this high velocity region that's also present in the Teleseismic S-wave model and the Teleseismic P-wave model. This low velocity region here between the Tintina fault and the Denali fault is present also in here in this model, Teleseismic S-wave model, and in the Teleseismic P-wave model. And also that the southern part of the northern Canadian Cordillera appears to be fast too. So now I'm going to go through some of the anomalies in high velocity regions or low velocity regions that we observe in our models and see how we interpret them. So I call that the seismic evidence for the Mackenzie Craton in Yukon territory. So here again, you have the shear wave velocity model at 100 kilometer depths obtained from surface wave data. And here you have the P-wave model and S-wave model at 100 kilometers depths, but using teleseismic data. And that they show basically that they're quite in agreement. So the transect UU prime is here running from here to there. And this one doesn't go to Banks Island, but it's not very important here. And what we see is that, again, this anomaly, high velocity region, high velocity anomaly labeled A tends to extend further deeper, like within almost the mantle transition zone. But again, we have some vertical smearing, so it's very difficult to characterize the vertical extent of this anomaly. So usually you just look at lateral resolution here because you know that they're going to be smearing in the vertical direction. And so here, if you look at the surface wave model, here what we see again is this very high region, velocity region, about 4.5 kilometers per second and higher. Now, if we compare with other geophysical data sets, so such as the magnetic anomaly map or the Bouguer anomaly map, we see that in the same location as where we have this anomaly labeled A, there is this high amplitude, long wavelength magnetic anomaly across northern Yukon and Northwest territories. That was called the Mackenzie River anomaly, the MRA, and was interpreted to be reflecting a very mechanically strong lithosphere that would basically resist against the thermal erosion that would occur on its western edge here in the Cordillera. Here with the Bouguer anomaly, we have some similar signal with a high amplitude, long wavelength Bouguer anomaly that could show, for example, that we had some denser crust here in the region, so more mafic crust in that case. And so when we put all those evidence together, so we have high velocities in this region, greater than 4.5 kilometers per second for shear wave velocities. We have suddenly a denser crust, a more mafic crust. We have a mechanically strong lithosphere in this region from the magnetic studies, regional magnetic studies. So they all point toward the fact that the northern Yukon is underlain by a cratonic lithosphere. And so that would support the existence of an exposed craton in the region. That's called the Mackenzie Craton here. And that would be basically the extent of the North American craton into the Cordillera domain. Now, if we travel south in northeastern British Columbia, and if you look at this anomaly labeled B, so that's the same depth slices for the same moles, just the transects is different now. So V is west, V prime is east. And what we see on this teleseismic P and S-wave moles and the transects here, we see that we have this very strong signal here showing this high velocity anomaly extending very deep into the mantle transition zone. So again, don't trust the depths, it's apparent depths. There's vertical smearing here in the region. And however, we see that this high velocity anomaly extends into the Cordillera here in the northern Canadian Cordillera. Same for this mole here. And same here on the shear wave mole obtained from surface wave data. And it's worth noting that this anomaly labeled B here was previously interpreted as a Cratonic lithosphere by J.P. Mercier et al. In 2009, where they used the same sort of technique, basically the same code, same inversion. And so, yeah, they interpreted the high velocity anomaly in that region to be a Cratonic lithosphere. So basically, the two labeled anomaly A and B here are interpreted to reflect some Cratonic lithospheres on both ends of the Cordillera deformation front. And so we came up with this schematical model here, where in gray you have the extent of the Canadian Cratonic lithosphere, and you see that it extends further west into the Cordillera with the Mackenzie Craton here, and further west also in northeastern British Columbia. And so what we think here is that the mantle flow is going northeastward here in the Cordillera, is channeled and guided beneath the Mackenzie Mountains, because those two Cratonic lithospheres here would act as basically buttresses against the intervening mantle flow. And so that would push towards the Canadian shield, the Cordillera material. And so that's why we would have this arcuate shape in the region. And that's why also we think that will control the deformation, regional deformation in this region. So now if we get back to the tectonic structures like the Tintina fault, for example, here you have a vertically average teleseismic P-wave mole, so between 66 and 300 kilometers depth. And the box here highlight the fact that we have a series of fast, slow, and fast anomalies between the Tintina and the Tenay fault. And so before going any further, I think it's important to mention that, because I'm going to also use some seismic anisotropy measurements. So a little bit of background before going any further, or I think some people can get lost here. So we use the SKS splitting analysis after. So what's SKS? So SKS waves are co-phases. So let's imagine that we have a source here. So the seismic travel path will be going down to the mantle as an S wave. It encounters the core mantle boundary, converts from S to P, then travels as a P wave into the core, the outer core, and bends up. And again, on its way up, encounters a second time the core mantle boundary, so convert from P to S, and travels as an S wave on the receiver side. So S, P, S, K for P in the outer core, SKS. So why do we use SKS waves? Mainly for two reasons, because we know the initial polarization, and because also any loss of energy, of the horizontal energy of the shear wave in the core constrain the observed splitting to be on the receiver side of the path. What does that mean? It means that basically if there is any signal in the data, it has to be due to seismic anisotropy on the receiver side here, just below the seismic station. But you can't really tell where, and you have to assume only one layer. But still, that gives you an idea of the average anisotropy, seismic anisotropy below your station. And so when entering an anisotropic medium, so that's what this little animation shows, you have a shear wave incoming, and it splits into two orthogonal shear waves, so the blue one and the red one. So you have a faster one, the blue, and the slow one, the red. And as you travel through the anisotropic medium, you see that basically the delay time between the two accumulates. And so the shear wave splitting is defined by two splitting parameters, which is the fast axis direction and the delay time. And so that's what I'm going to show now on top of my tomographic models. So here you have the splitting parameters plotted on top of the tomographic mode, the P-wave, Teleseismic P-wave mode. So the length of the bar here gives you an idea of the magnitude of delay time. And then the orientation of the bar gives you the fast axis orientation. So the gold bars is a compilation of available seismic anisotropy measurements across northwestern Canada. And the orange bars here represent seismic anisotropy measurements that I've done myself. And so what we observe here along those three transects, so the boxes represent the splitting that I'm going to plot in cross sections right after. And on those two transects that are perpendicular to the Tintina and the Tenay fault, you see that the splits, they tend to rotate, and as we get closer to the Tintina fault. And this is accompanied with an increase in delay time. So for the stations that are on top of the Tintina fault, we see delay times of 1.5 2 seconds. And so that suggests that deformation occurs in the entire lithosphere. For the south, we have this transect showing something different here, where the fast axis directions, they tend to align with the Canadian shield fabric here. And so that was interpreted to reflect the Cratonic lithosphere extending west of the Tintina fault here. And so now the same thing, but in cross-section view. So you have the 3 transects here, A, B, and C, and A is here, B is here, and C is here. Again, and A and B are perpendicular to the Denali and Tintina fault. The Denali Tintina fault are shown on this transect here. So that's the topographic profiles here on top. Then you have the splitting parameters, so the delay time and the fast axis direction, and then the cross section through the P-wave mole. So the horizontal the horizontal brown lines here shows the absolute motion of the North American plate and the Pacific plate. And the green horizontal line gives you the approximate strike of the Tintina fault here at the cross section. And so what we observe again is that we have this rapid increase in delay times as we approach the Tintina fault, but also as we approach the Denali fault. And we observe this rotation of fast axis direction here as we approach the Tintina fault and the Denali fault. Along transect BB prime, it's even more convincing as we see that this rapid increase at the Tintina and the Denali fault, and this again rotation of the fast axis direction as we get closer to the Tintina and the Denali fault. And so that's also collocated with this sharp P-wave velocity gradients at depth. So you see we have this vertical boundary here between a high velocity region, a low velocity region, high velocity region, and it's more complicated here. And same here. However, on the CC prime transect, we see that the delay times, they tend to decrease as we get closer to the Tintina fault, and they almost go to nothing. And we don't observe any rotation as we cross the Tintina fault. They tend to be similar to what's observed in the east, in the eastern section of the transect here. And so that was interpreted to be some interferences between the Tintina fault and the Canadian shield fabric. So long-term shearing fabrics in the Canadian shield fabric, which is still consistent with lithospheric-scale shearing. And so what we think here is that cannot be just the explanation cannot be only due to a thermal anomaly. It has to be due to different mantle compositions. And so the question now is, do we have other evidence of lithospheric-scale shear zones around the world? And basically the answer is yes. So 3 different examples here. One from Ian Bastow in 2007. We are in Scotland. There is the Glen fault here, Great Glen fault. And you see that the splits are represented by this yellow arrow, double arrows here. And you see that they tend to rotate as we get closer to the Great Glen fault. And that's also accompanied with increase in delay times. Here we are in Tibet with the Altin-Tag fault. And again, we see this rotation as we get closer to the Altin-Tag fault, and same thing with the Kunlun fault here. And we observe something similar with Duclos et al. In 2005 in New Zealand, where we have the splits. So that's from PN anisotropy. That's slightly different, but showing the same thing. They tend to rotate here to be parallel to the Alpine fault in New Zealand. So now if we assume that the Tintina fault is a lithospheric-scale feature here, we know that there was a large amount of displacement occurred on the Tintina fault. And that was reported in Gabriel et al. In 2006, about 430 kilometers of horizontal displacement. So what we've done here on this figure is we just restored those 430 kilometers across the P-wave mole. And so what we see after restoration, so that's this figure here, we see that we have a good alignment and continuity of P-wave anomalies across the Tintina fault, especially for the past P-wave anomalies, so labeled D and F here, which basically outline the North American Craton margin. So this high velocity P-wave anomaly that's located here, that was labeled D, that is currently in eastern Alaska, has been observed by over regional teleseismic tomography moles over Alaska. So that's a mole from Martin Short et al. In 2016 in JGR. And so here you see we have a very high velocity anomaly that corresponds to the Aleutian subduction zone at 100 kilometers depth. And each black dot represents a seismic event, which is related to the subduction zone, basically. And And you can see that there is no dots in this red circle here. So they interpreted that as an aseismic region of the Pacific slab in that case. So we proposed here an alternative explanation for this high velocity anomaly. We propose that this fast P-wave anomaly structure, which is currently located in eastern Alaska, represents a fragment of the Mackenzie Craton, and that has been chiseled and displaced to the northwest by the Tintina fault between Lake Cretaceous and the Eocene. Another feature that we observe in our model is this low velocity feature here. We have this low velocity region in the shear wave velocity model obtained from surface wave data. And that's very well bounded by the Tintina here and the Denali fault here. And so here, when we look in cross section, so CC prime here runs perpendicular again to the Tintina fault. Here is the low velocity anomaly. So if we zoom in the uppermost mantle structure, seismic velocity structure from 40 to 100 kilometers depth, and so we change the color palette here, we see that basically the low velocity anomaly is very well defined. It has a very sharp boundary to the east, and that's collocated with the Tintina fault, and perhaps to the west with the Denali fault. And there's maybe something happening also at shallow depths here. And what's very interesting to note is that in our Teleseismic S-wave model, we retrieve the same signal here. So that's exactly the same location. And we observe this vertical low velocity anomaly extending deeper and deeper. And so here, what we suggest is that this shows an upwelling of deeper and hotter asthenospheric materials that filled voids following the 430 kilometers of a lithospheric scale motion by the Tintina fault between 65 and 35 million years ago. So also what we note is that here, as I said earlier, the black dashed line shows the input MO, and the white dashed line here shows the output MO obtained from the inversion of surface wave data. And you see that the crust is thinner on top of this low velocity feature here. So that could mean that we are having some thinning, like thermal erosion at the base of the crust here. And what's also interesting to note is that there is some volcanoes in that region here that are part of the northern Canadian volcanic province. So that could be potentially a source, because we know that those volcanoes have an asthenospheric source here. But unfortunately, if you know the northern Canadian volcanic province where it is, it extends further south in the Canadian Cordillera. So it cannot explain the magmatism here for the entire northern Canadian volcanic province. So in conclusion here, we saw that we have geophysical evidence that possibly confirm the presence of a buried craton, the Mackenzie Craton, across Yukon and Northwest Territories, which is the extent of the North American Craton into the Cordillera. We have two mechanically strong cratonic lithospheres that act like trusses on both ends of the Mackenzie mountain frost belt. So that's this part of the Cordillera deformation front again. The Tintina fault appears to be a newly identified lithospheric-scale shear zone. We interpret a high velocity anomaly to be a cratonic fragment that has been chiseled and displaced to the northwest by the Tintina fault between the Cretaceous and the Eocene. And lastly, the low velocity region that we observe between the Tintina and the Denali fault at upper mantle depths reflect upwelling asthenosphere, which likely postdates 430 kilometers of previously estimated Eocene lithosphere scale horizontal displacement along the Tintina fault. And that's it.